Alright, so we're going to go over Chapter 7 today, just molecular and cellular radiation biology. We're going to hit just a few of the high points on this. It's been a while since I've kind of gone over this. And I know several of your other classes have kind of covered some of this material already, but I want to go over a few key points on here. Definitely read over the slides. Each one of these slides has been put together to kind of just hit the high points of the chapter. Radiation energy transfer determinants, basically the three of them on there: linear energy transfer, relative biologic effectiveness, and oxygen enhancement ratio. Just determinants determine how effective the radiation is. Linear energy transfer, average energy deposited per unit length of track by ionizing radiation as it passes through and interacts with the medium on its path. So basically, as the radiation goes through the body, the little energy that's going to go through is going to be measured in these tracks. And tracks are just these little measured off areas, like a centimeter or an inch at a time, and they just kind of average those through. Usually described in keV per micron. Low LET radiation, which are X-rays, which is what we're mainly dealing with, causes indirect damage to tissues, which usually can be reversed by repair enzymes. So high LET radiation, which are the higher energies, alpha particles, ions of heavy nuclei, and so on, can cause irreparable damage to DNA because of multiple strand breaks in DNA. It cannot be undone by repair enzymes are possible. So with this amount of radiation, why the regular ionizing radiation is a little bit safer is because it causes that indirect damage. So normally the enzymes can repair that portion of the cell which has been kind of disrupted. We'll get into this a little bit more following later in this chapter. RBE, type of radiation being used, ratio of dose of reference radiation, which is conventionally the 250 kVp, to the dose that is necessary to produce the same biologic reaction in a given experiment. So this is mainly for experiments to kind of compare them, make sure that we know what kind of dose the patient is getting. The reaction is produced by a dose of test radiation delivered under the same conditions. So you'll typically get a question like this, calculating the RBE. Generally, you're just going to divide the two numbers, the 40 by 8, to give you the relative biologic effectiveness of 5 in this particular case. Don't be confused with 250. That's usually the pretty standard keV they're going to use to produce the same effect. So they're asking what the effectiveness is, just divide what it takes. So what it would be a higher number, generally divided by the lower number, which will produce the same effect. So LET of radiation increases, so the biologic effects. RBE quantity describes this relative effect. So this just basically describes what RBE does. Oxygen enhancement ratio. This is basically kind of an experiment done when you have aerated conditions versus when you remove the air, which will give you a hypoxic condition on there. So it's basically another experiment to kind of figure out, how effective radiation will be under those kind of terms. Aerated condition, photon 2.5 to 3 times more effective, or hypoxic, only 1/3 as effective. So really, it's just if you have a registry question that talks about a ratio, they're almost always talking about oxygen enhancement ratio on there. So molecular effects, molecular cellular organic levels. Getting into kind of the main portion of this, radiation action on the cell is either direct or indirect depending on the site of interaction. So depending on where it hits, basically, will determine whether it's direct or indirect. Okay? Action is direct when biologic damage occurs as a result of the ionization of atoms on DNA, causing them to become inactive or functionally altered. So that means when you have some radiation coming in and it gets past all the kind of the water molecules and hits directly on the main portion of the DNA strand, that would be a direct action on the cell. Action is indirect when effects are produced by relative free radicals created by the interaction of radiation with water molecules. These free radicals can cause substantial disruption to DNA molecules, which results in cell death. So what happens with indirect damage is that the radiation will come in, it will interact with the water molecule because you have 80 to 85% of the cell made up of water, and then what that'll do is that will take the H2O or H2O, kind of remove an electron from that, and maybe you just have a single hydrogen
atom and the single oxygen atom now, so it's a little bit more unstable, and then you have this reaction with the DNA strand at that point. High LET radiation more likely to cause biologic damage from direct action than is low LET. It just has more power, so it's a little bit tighter in its path going through the material of the body. Most X-ray damage to macromolecules is a result of indirect action, though. It's because of the presence of water, like we mentioned on this. This visual slide here kind of sums it up a little bit more. The radiation photon coming in, reacting right on the DNA helix, as opposed to indirect action, where it will react with this water molecule, and it'll give you a free radical, and then that free radical actually in turn hits the DNA helix as well. Point mutations, we're not going to cover that too much. Double strand breaks associated with high LET radiation, repair of this type of damage is not likely to occur. So if you have high LET, basically that's a lot of radiation going through a very small area, and that you have a lot of radiation going through, it's got a lot of power to go through it, and it will actually break both sides of this kind of DNA ladder, which we can see here with a double strand break going across on here. So these are all kind of linked in together with the double helix. So if only one side is broken, like a single strand break, then it's less likely that the cell will die. It still has enough repair enzymes on both sides to kind of repair this and make sure to kind of reestablish the cell. Target theory states that when the cell DNA is directly or indirectly inactivated by exposure to radiation, the cell will die. So indirectly or directly. So that usually affects the cell nucleus, okay, which is significantly damaged by exposure to ionizing radiation. The cell can die, experience reproductive death, so it's unable to reproduce itself now, especially the germ cells of the ovum and the gonads, or chromosome breakage on that. Cell survival curve, these are mainly used in radiation therapy to kind of determine the sensitivity and see what types of radiation will work on killing the actual cancer cells without destroying every other cell within its path as well. Law of Bergonier-Tribondeau. This is an important concept to get because the ART does cover this quite a bit. You do need to know this entire portion here with a differentiation, but basically what this says, it states that radiosensitivity of cells is directly proportional to their reproductive activity and inversely proportional to their degree of differentiation. So really, if you're thinking about germ cells within the ovum and the sperm, basically you have the reproductive activity is very high because it's constantly splitting and creating. So if you think about the egg that women have, that's changing every month or 28 days pretty much. Sperm cells changing pretty much daily in men. Most pronounced radiation effects occurs in cells having least maturity. So the least maturity, that means they're creating new cells constantly. Specialization, so germ cells, or not germ cells, stem cells are a little bit more kind of a blank cell that's waiting to be specialized. Those are a little bit more sensitive as well. Greatest reproductive activity, longest mitotic phases, goes into mitosis, meiosis. True for all cells within the body, explains that the embryo fetus is more susceptible to radiation damage. So when you have a woman that is pregnant, you have all these cells that are very immature, not quite specialized yet. They're basically creating a baby, and that's why we need to shield constantly the lower halves of men and women, because those cells are kind of going through a lot of changes, and they're a bit more sensitive to the potential effects of radiation than any other cells. If you think about like the muscle cells, those cells are not really reproducing. The specialization, they're really just specialized just to move the muscles. Brain cells, same thing. Those are not undergoing rapid changes as well. So if you think about it and how the cells actually work and their level of maturity, it makes sense that we are going to shield the gonads as much as possible. LD5030, this is just describing the lethal dose, is what this means. It would kill 50% of the subjects within 30 days. For humans, numbers are usually 50% within 60 days, so that number is more accurate at LD5060. 3 to 4 grays, about 300 to 400 rads is most likely to cause this. The reason for humans why it jumps from 30 to 60 days is because of the presence of medical intervention. So medically induced comas, antibiotics, oxygen chambers, all those things can kind of stretch out that time. So they're not going to say you're out of the woods after 30 days if you have that type of radiation. They're going to wait till about 60 days to actually make any determination of how much danger you are still in or how likely you are to recover. Lymphocytes, these are just blood cells that basically have a 24-hour life. It depends against foreign antigens by producing antibodies to combat diseases. It's a subgroup of leukocytes, so it's kind of within the body. We're not going to shield, obviously, everything within the body, but they kind of run around the whole body, just kind of protecting yourself. 25 rads is enough to sufficiently depress the number of cells present in the circulating blood. So if it's depressed, that means they're not going to be not doing their job, and basically you're open to other diseases. Common colds, most likely, will run rampant if these lymphocytes are sufficiently depressed by a severe amount of radiation. Sure, read over the reproductive cells. That's on page 152 and 153. A couple of videos have been posted on mitosis and meiosis. It's been probably a little while since some of you have taken biology, so it just describes the differences between the two and how the cell division actually is created. And it goes into effect of the germ cells pretty well to explain the differences and why they're a little bit more sensitive than other cells within the body. You see this, time to leap work, obviously. Hopefully none of you will ever see that. Hopefully you all get the reference on that, but it is a joke. Don't go looking around for it. This chapter is a little disjointed. It's going to take me a little while to kind of get back in the swing of this radiation biology info because I haven't taught it in a few years. But if you have any questions, then certainly send me a message. I don't know that I'm going to be in class to kind of go over these things very well. We will have some office hours here and there if you want to kind of go over some things that you're just not quite getting. Next week we're going to be going over the deterministic effects, stochastic, non-stochastic, which is a little bit more interesting. This can be a little bit drier material, but as I said, if there's any particular area that you don't understand, then feel free to ask. Hopefully we'll have a few more PowerPoint presentations to kind of go into a little bit further explanations of this. But like I said, they'll be a little disjointed and a little uneven and not quite as polished as maybe some of the other PowerPoints I've posted in the past. But we'll all just have to deal with that. Have a good day.